And here we have another What the Physics video. It's more on graphing for kinematics. Now we're going to be talking about position time graphs and velocity time graphs, and we'll sneak in some other ways of representing what's going on here. But first, learning targets. I can translate between, or is it among? A position versus time graph, a velocity versus time graph, a motion dot diagram, and a verbal description. Oh yeah. So, speaking of verbal descriptions, we've got two graphs below showing the same situation. As we can see, this one over here is a position time graph, then we have a velocity time graph, both for walking to school. So a student is walking to school, it's 80 meters from home. So their home is considered the reference point, and they're chugging along at a constant velocity of 1.33 meters per second. So I can clearly see, hey, yeah, I started at 0 and I move a total of 80 meters in 60 seconds. Okay, good. Now, if I take a look at this position time graph and look at the slope, I can say that the slope is positive because it's like we're going up the hill, and the slope is constant. Now, a lot of people will say, oh, no, the slope is increasing, right? Because it's going up. No. It's a straight line. Slope is a straight line, which means the slope is constant. Straight line slope means constant slope. Okay, so what we're going to do is we're going to take this sentence here. The slope of the position time graph is blank and blank. And I'm going to put in a new sentence here with the velocity is blank and blank. So whatever words I use to describe the slope of the position time graph, I will use to describe the velocity. So the velocity is positive and constant. And that's what I have right here. The velocity is positive and constant because the slope of the position time graph is positive and constant. If the slope of the position time graph were negative and constant, then that means the velocity would be negative and constant, and so on. Okay, so there are different ways we can represent what's going on, and it's very, very important that you can express yourself pictorially as well as mathematically and such. So here we have our dot diagram. Now we don't typically have to have numbers along the bottom here, but just to help you visualize, okay, 0, 1, 2, 3, and so on. From here, I can definitely see that I've got a bunch of dots, and we're assuming that the dots are spaced at or are coming out at regular time intervals. Let's just say 1 second. That's not really important right now, but let's say 1 second. So in every 1 second time period, we have traveled 2 meters, 2 meters, 2 meters, 2 meters, and to the right. So that means my velocity is going to be nice constants, and it's going to be positive, right? So my velocity, which is in meters per second, or this graph happens to show it as meters times seconds to the -1. It's meters per second. Anyhow, this velocity time graph is showing a nice constant positive velocity. Constant velocity because not going up and down, right? But the velocity is positive because we're above the horizontal time axis. How do I get that from my position time graph or my displacement time graph? Okay, remember the slope of the position time graph is the velocity. I said the velocity is positive and constant. That means the slope of my position time graph is positive and constant. Okay, so just use this sentence. The slope of the position time graph is, you use whatever descriptors, positive and constant. That means the velocity is positive and constant. Now, what if we have a negative and constant velocity? Ooh, what will that look like? Well, hey, it's just the arrows are going in this direction. Yeah, really complicated. Okay, what's going on here? Well, my velocity is negative and constant. Remember, it's a velocity time graph. Constant velocity just means we're not going up or down. Negative means we're below the horizontal time axis. Okay. On a position time graph, or displacement time graph as sometimes we call it, on the position time graph, the position doesn't have to be negative in order for our velocity to be negative. Remember, velocity is change in position divided by change in time. So it just means our slope here has to be negative. So if I look at this, the slope of the position time graph is negative because it's like we're going down a hill, and constant because straight line. Then that means my velocity is negative and constant. So, all right, that's cool. That's cool. I like it. I like it. And this came from a friend of mine. It's a whole list of ways to keep track of what's going on. This is for a velocity time graph. Remember, anytime you see a graph, you say, what type of graph is it? Velocity time graph. Velocity and time. And this is, it might be kind of busy, so these are some like summary points. On a velocity time graph, if we have a horizontal line, that means a constant velocity. We saw that here and on the previous slide too. Okay. Number 2, any slope means there's going to be a change in velocity. We should clarify any non-zero slope is going to be a change in velocity. So this here and this here and this, this here and this here, all those mean the velocity is changing. In this case, we're getting slower. In this case, we're getting faster. Faster, slower. The y-intercept of a velocity time graph is going to be my initial velocity. Just like the y-intercept of a position time graph is going to be my starting position, right? It's going to be your starting whatever the value is. If I had an acceleration time graph and I said, what's the y-intercept of that? That'd be my starting acceleration. Well, we're not really going to deal with changing acceleration, so meh. Okay, number 4. Closer to the x-axis, the horizontal, means slower. Further away means faster. So here is something that I kind of mentioned earlier, but it might be a little bit confusing to people. So quite often we think of positive is larger than negative because that's what they show you in math class. On a number line, they say, oh, anything up here on the positive side is going to be bigger than anything on the negative side. If I have positive 10 apples, that's a lot of apples, right? If I have negative 20 apples, that'd be like, oh, I owe someone 20 apples, so I have a loss of something, right? Well, that's on a number line. In physics, when the positive and negative are really just talking about direction. So if I'm going north on 28 at 35 miles an hour, let's say I'm going north on 28 at 35 miles an hour, so that'd be positive 35. And if I'm going south, or let's say you go south on 28 at 40 miles an hour, well, that'd be south, that'd be negative. So I'm going positive 35. You're going at negative 40. Which one of us is traveling faster? You are. You're the one going at negative 40. I'm only going at positive 35. Yeah, mine is positive, but positive 35 just means 35 miles per hour north. You're negative, that just means south. You're still going faster than me. Okay, so getting farther and farther away from the horizontal axis means you are going faster, whether it's in the upward direction or the downward direction from the horizontal axis. Let's see, what else? Steeper slope of a velocity time graph means greater acceleration. The area under or to the x-axis, the horizontal axis, of each segment is the displacement. We haven't discussed that yet, but the area under the curve of a velocity time graph is going to be displacement. Okay, let's see, the slopes are reversed going leftward or rightward. So that's the whole like, oh yeah, I'm going faster as I come up here. I'm going faster as I'm going this way. The farther away you are from the horizontal, the faster you're going. That's for a velocity time graph. Okay, and any lines that cross the x-axis or the horizontal axis means that for a split second at least, your velocity will be hitting 0. So I might have a positive velocity, slowing down, 0 for just a moment, and then speeding up, but in the negative direction. Okay, yeah, that's cool. Physics, yeah. Okay, so let's look at this. I have various ways of expressing what's going on. So think, pair, share. How many ways can you express it? So what is it? The motion. Well, what do I have? I've got this dot diagram. I have this dot diagram, and what can I tell about the dots? Are they evenly spaced? Are they getting farther apart? Are they getting closer? They're definitely getting farther apart, so that means I'm traveling faster. I'm speeding up right over here. let's see. So speeding up. Okay, and then what about this area over here? Well, the dots are not getting farther apart. They're not getting closer either. So this is a constant velocity. Okay, I'm just moving in the positive direction. My speed is constant. That means my velocity is constant. Okay. All right, so on a position time graph, how am I going to show this? Well, I'm not going to plug in any numbers here or anything because I don't actually have any positions. You could argue, oh, maybe you have times. We're just gonna kind of chop it into halves here. Okay, we're gonna chop it up and we're gonna say, okay, for the first half we are speeding up. You know what? Let's actually start with the velocity. I think velocity is easier to do. The velocity time graph is easier to do. So for the velocity time graph, for the first half, approximately, I am going to be increasing my velocity. So I started at 0. Where's my mouse? Here we are. I'm starting at 0, and I am increasing my velocity. There. And then what? So that was for this section over here. And then for this section over here, I'm going to be keeping a nice constant velocity. Nice constant velocity. Whatever that value was that I kind of ended at there. So this is supposed to be a horizontal line right there. There, horizontal line. Okay, so my velocity is increasing because on my velocity time graph, I'm moving farther and farther away from the horizontal in the positive direction. And then for this section, nice constant velocity, still moving, just at a nice constant velocity. So how am I going to draw that out on a position time graph? Well, the slope of the position time graph is the velocity. So if my velocity here is positive and increasing, my velocity, not the slope, but my velocity is positive because we're above here, above this line, and increasing, that means my slope should be positive and increasing. The slope of my position time graph should be positive and increasing. Now, I don't know my initial position. I'll just treat it as 0 because that's what we said over here. So the slope here should be positive and increasing. So up to there, okay? Positive and increasing slope. And then my slope for this second half, so this is, it's tough to tell. It's a bit of a curve to it, okay? Then for the second half, my slope is going to be a nice straight line. Okay, that's kind of difficult to tell, so I'm just going to tell you that this is a straight line. Straight line. And then this one here is an upward curve. Okay, all right, so there we go. And then you can, of course, write out a nice description in words like, what was going on here? Car was driving along, a car was at a stop sign, and then it speeds up and goes up to, let's just say, 20 miles an hour, and then just continues on at 20 miles an hour. So the car was speeding up here, and then it just continues at a nice constant velocity right there. Okay, now we're going to kind of skip ahead just a little bit. We can do those in class, maybe. All right, so now we're going to talk about velocity versus time graphs. So remember, anytime you see a graph, what type of graph do you have? I have a velocity time graph. How do I know? Well, it's not labeled here. How do I know that? Well, look at the axes, velocity and time. Okay, so if I had a position versus time graph, I knew I could get velocity by taking the slope, because I know that velocity is displacement divided by time, change in position divided by change in time. Okay, well, I know acceleration is delta v over delta t, so stands to reason I can just take the slope of this here velocity time graph and I'm going to get acceleration. Oh yes, that is what I will be doing. So let's go ahead and do that. So what is the average acceleration from 0 to 4 seconds? Now be careful, this is a little bit sneaky. I did chop this up into sections, okay? So let's see, mousey, there we go. So from 0 to 4. So let's see how straight a line I can draw with this thing. Oh, that's pretty good, actually. So what is the slope of this line here? Slope, question mark. Okay, so slope is rise over run. So I know that acceleration, which is delta v over delta t, that's going to be my final minus initial of each one, final velocity, v final minus v initial over t final minus t initial. Okay, so my v final is going to be 2 meters per second, 2 meters per second, minus 0 meters per second, that was my initial, meters per second, divided by my time final, that was 4 seconds, minus 0 seconds. Okay, so in other words, 2 over 4, that's 1/2, right? And then meters per second divided by seconds is going to be 0.5 meters per second. Delicious, delicious. Now, that was for this line here. What if I wanted to take the slope of the individual lines? What if I wanted to find the acceleration for these smaller segments? How would I do that? Well, what's the slope of line A? Okay, the rise is 4 meters per second. The run is 2 seconds. So 4 divided by 2 is going to be 2. And then that's going to be meters per second over seconds, meters per second squared. 2 meters per second squared. What about for line B? Slope is 0. So that means acceleration is 0. What about for line C? Line C, well, I know that the slope is negative, so my acceleration is going to be negative. Let's actually do the math, right? Final minus initial. 2 meters per second minus 4 meters per second, so that's going to be negative 2 meters per second, divided by 1 second. Negative 2 meters per second squared for line C. Now notice, if you are thinking about this and you say, oh, wait a minute, let me just average these out. Negative 2 and 0 and positive 2. Wait, those don't average out to be this, to be 0.5. How did that work? Well, keep in mind, and you got to be very careful with this sometimes, these time intervals were not the same throughout. I spent more time going at 2 meters per second squared, this one here, than I did at 0, and then I did at negative 2 meters per second squared. Okay, so if you're looking for the average acceleration, you can't just take the different values and add them up and divide by the number of values. You do what we just did. You use the actual formula. Final minus initial for velocity divided by final minus initial for time. Physics. Man, this is some good stuff. Some good stuff, but we do have to be focused here, right? Indeed. Okay, and then let's see, we can do this. I think we can do this one in class. All right, so summarize the reading a graph part 1. The idea behind this is, of course, you can do your learning targets, which were, I can translate between or among a position versus time graph, a velocity versus time graph, a motion diagram, and verbal descriptions. Look at that, I even snuck the velocity into acceleration in there. Fair. So sneaky, but it's for physics, so you gotta love it.